Okay, let's unpack this. Welcome to the deep dive. Today we're plunging into some really fundamental questions about energy. Can alternative sources like solar and wind truly meet all our power needs? Is distributed generation, where power comes from lots of small local sources, is that the future that replaces our big traditional grid? Or, as the source we're looking at argues, is the real solution still rooted in a systemic, centralized approach?
That's right. We've got one key source for this deep dive. It's a video that presents a very strong case about these exact topics, and it challenges some common assumptions along the way.
Yeah, definitely. And our mission is to take everything in that video, the data, the arguments, the sometimes, well, surprising perspectives, and distill the core ideas to help you understand this complex world of energy systems.
Makes sense. We should probably start where the source does, right? With the basic definition. What even is an energy source?
Good point. It defines it simply as a naturally occurring substance or process humans use to get needed energy.
Like wood, coal, gas, oil, the traditional stuff that, powered the industrial age.
Exactly. But the video quickly pivots to the environmental cost of relying so heavily on those. The CA2, the greenhouse effect, global warming, that whole issue.
And that's really the driving force behind the search for alternatives, isn't it?
Absolutely. Which leads us straight into the main players in the alternative energy space that the source discusses: solar, wind, hydro, and geothermal.
Right, those are the big ones. But it also gives a nod to some more out there possibilities, too.
Oh, yeah. Like what?
Things like tapping into volcanic energy. Tornadoes imagine that atmospheric electricity, temperature gradients in the ocean, and even osmotic diffusion.
Osmotic diffusion, mixing fresh and salt water.
Yeah, exactly. Fascinating ideas, but the video really focuses on the ones making an impact now. So maybe we should dive into solar energy first.
Sounds good. The source highlights that solar is now being used pretty widely. I think it said over 80 countries globally.
Yeah, something like that. And the installed capacity is significant, over 770 gigawatts worldwide, which sounds like a lot.
But there's always a but, isn't there?
Well, the video is quick to point out that's still only around 3% of total global energy generation right now.
Only 3%. Wow. Despite that relatively small percentage, the sheer potential is immense, right? The source mentions the Earth gets enough solar energy in just one single day to power the entire planet for a year.
It's staggering potential. And the source highlights the traditional leaders in solar, Europe, China, the US, but also notes these emerging players stepping onto the scene. Countries like Kazakhstan, Kenya, Saudi Arabia, Egypt were mentioned.
Interesting. And we're seeing innovation too, like those floating solar farms. The source talks about them in South Korea and Chile. What's the thinking there? Is it just about space?
Partly space, but the video suggests other potential benefits, like the water cooling the panels, which could improve efficiency, and maybe reducing evaporation from the reservoir. Sometimes maintenance access might even be simpler,
Well,
apparently.
but I guess if it's on salt water, you run into issues like corrosion or salt.
Exactly. The source notes that saltwater spray can leave a salt film, requiring constant cleaning. And actually, that cleaning problem seems to be a major recurring theme for solar infrastructure in general, according to the video.
You mean just keeping them clean from everyday stuff?
Yeah, dust, moss, bird droppings, hail damage, snow cover, they all cut down efficiency and need consistent maintenance. And you need people who know how to do that maintenance properly.
Right. The source used that example of the ambitious desert project, the one planned for the Sahara that didn't really move forward. What specific solar challenges did that project run into, according to the video?
Well, beyond the massive challenge of just building the transmission lines, the energy bridges to get the power out, the video points to two main operational hurdles. First, the relentless dust and sand constantly covering everything.
Constant cleaning needed then.
Absolutely. And second, the practicalities. Security in such a vast remote area and finding enough qualified people willing and able to work out there to do the maintenance. The source frames these as pretty significant blockers, not just minor issues.
So it's really not just about generating the power, it's keeping the whole system running reliably day in, day out, in often harsh conditions.
Precisely.
Stepping back for a sec, the video touches on the history too, doesn't it? Understanding solar energy itself was quite a journey.
It really was. The source takes us way back to 1839, Becquerel's experiment, where he first observed the photoelectric effect, basically, light making electricity.
And then Einstein comes along in 1905, provides the theoretical basis with his work on photons, which actually won him the Nobel Prize later in 21.
Yeah, understand the why and how was crucial. And that scientific understanding eventually led to the first practical silicon solar cell. That was Chapin, Fuller, and Pearson in 1954.
What kind of efficiency did they get back then?
Pretty modest by today's standards, only about 6%, but it was groundbreaking at the time.
And almost immediately, that tech found a really critical early use, right? Powering satellites in space.
Exactly, where you couldn't exactly run a power cord or haul up fuel easily.
Okay, so looking at solar through the source's lens, summing it up, what are the main positives and negatives it really hammers home?
On the pro side, pretty clear. It's renewable, it's quiet during operation, and once it's up and running, the operation itself is clean. No greenhouse gas emissions coming directly from the panels converting sunlight.
Okay, but the source seems quite emphatic about the challenges too. What's the biggest one?
Intermittency, hands down. The sun isn't always shining, clouds happen, night happens. So you absolutely need a way to store that energy. You need accumulators, batteries, some kind of buffer.
Right, and equipment cost is still a factor, even though prices have dropped a lot.
Still a factor, yes, though definitely improving. But here's where the clean aspect gets a bit more complex, as the source highlights.
How so?
The environmental cost of manufacturing the panels. The process involves some pretty toxic substances, and it relies on extracting rare earth metals. And the video points out that the extraction processes themselves can be environmentally damaging and, frankly, dangerous for workers.
Ah, so clean operation doesn't automatically mean clean production. That's a really important distinction.
Definitely. And the source adds another layer. We still haven't fully figured out how to ecologically recycle old solar panels on a massive scale. What do we do with them all at the end of their life? That's a growing problem.
So it paints a much more nuanced picture than just saying solar is clean energy.
Exactly. It's cleaner in operation, but the life cycle impacts are real concerns, according to this source.
Okay, let's shift gears then. Wind energy. The source explains this is fundamentally converted solar energy too, right? In a way.
Yeah, that's the basic physics. The sun heats the earth unevenly. That creates pressure differences in the atmosphere, and boom, you get wind.
And the mechanism for capturing it is pretty straightforward. Wind turns the blades spin a generator inside the nacelle.
Right, and the video mentions an interesting technical point. The raw AC power coming straight from the generator is kind of dirty. Its frequency and voltage fluctuate with the wind, so it needs to be conditioned.
How do they do that?
It goes through a rectifier to convert it to DC, and then an inverter to turn it back into perfectly stable, clean AC power at the right frequency and voltage for the grid.
Gotcha. And wind power is seeing massive growth globally, isn't it? The source mentions China taking a really strong lead.
Oh, huge. They have enormous projects like the Gansu wind farm, plus ambitious plans for offshore wind. And globally, the growth is rapid. The video cited 2020 figures, I think, adding 93 gigawatts of new wind capacity worldwide in just that year.
Wow, and some countries already get a really substantial slice of their electricity from wind. The source mentioned Denmark.
Yeah, Denmark apparently got 48% of its power from wind back in 2019. Ireland was at 33%, Portugal 27%. Pretty impressive penetration in some places.
People have used wind for ages, obviously. Ancient Egyptians for sailing, Europeans with windmills for grinding grain. But the story of the first wind electric station is kind of wild, as told in the source.
Right, that was Blythe in the UK way back in 1887. This guy builds a 9-meter windmill, hooks up a generator.
And offers the extra electricity to light the town. Seems pretty forward-thinking.
You'd think, but apparently the townsfolk rejected it. The source says they called it the devil's work.
No way, the devil's work.
Hard to believe now, right? And the source points out that even though he eventually used it to power a local hospital, the technology was basically deemed unpromising at the time. It took until 1951, decades later, for the next significant wind station to appear in the UK.
That's incredible. The video also makes an interesting observation about the design, why those big turbines almost always have 3 blades.
Yeah, it draws a comparison to 3-phase electrical systems, suggesting 3 is kind of the sweet spot aerodynamically. Fewer blades might miss too much wind, more blades add weight and drag without proportional power increase. It's about finding that optimal balance.
Makes sense. Okay, so pros for wind, according to the source. Renewable, no operational emissions, similar to solar in that respect.
Correct. But the cons, again, echo some of the solar issues. Intermittency is a big one. Wind speeds fluctuate. Sometimes it doesn't blow at all. So again, you need those accumulators or some other way to balance the grid.
And a significant issue they bring up, which is maybe different from solar, is noise.
Yes, audible noise, but also, importantly, low-frequency vibrations or infrasound. The source states this is a major reason why residential areas are typically kept far away from large wind farms. These vibrations can apparently affect both humans and wildlife in ways we're still understanding.
Okay. So those are the big two alternative sources the video really focuses on. But let's briefly touch on a couple of the more exotic ones it mentions. Atmospheric electricity, for instance. That sounds sci-fi.
It does. And the theoretical potential is just mind-boggling.
Yeah.
The source estimates it at something like 10 to the power of 7 gigawatts, vastly more than current global needs.
Why aren't we tapping into it? Seems like free energy from the sky.
Well, the source explains it's incredibly difficult to capture, reliably and safely. It walks through some history. Franklin's famous kite experiment. Tesla had conceptual ideas. And there was a guy named Plowson in the 1920s experimenting with specialized balloons to collect charge.
And they didn't pan out because...
Basically, they were bulky, dangerous, wildly impractical, and couldn't consistently extract a usable, stable amount of power. The source does mention some potentially new research from a university in Brazil looking at the physics of it, how charge is released from water droplets.
But the fundamental problems remain huge.
Exactly. How do you safely and efficiently get that immense energy down to the ground? And the source raises a really serious concern, the potential risk of messing with Earth's natural global electric circuit. Doing so could have unpredictable, maybe even catastrophic climate consequences, triggering storms or droughts elsewhere.
Yeah, that sounds risky.
And, as the source puts it rather bluntly, while fossil fuels are still relatively easy to get and use, nobody's seriously pouring massive resources into this incredibly difficult and potentially dangerous path right now.
Fair enough. What about that other one, osmotic diffusion, mixing salt and fresh water?
Yeah, the source mentions this as a very niche method. It's based on the energy released, the entropy change, when fresh water mixes with salt water. Apparently, there's only one known operational station using this tech, somewhere in Norway. Interesting physics, but probably not a widespread solution.
And gravitational energy systems. The source talked about things like lifting heavy weights.
Right. But the source clarifies these aren't really generating new energy in the way a power plant does. They function primarily as energy accumulators, energy storage.
Ah, storage. So they fit into that picture of needing ways to handle the intermittency of solar and wind.
Exactly. The idea is when you have surplus solar or wind power, you use electric motors to lift a huge weight, maybe up a tower or out of a deep shaft. You're storing that excess energy as potential energy.
And then when the sun goes down or the wind stops,
You let the weight descend under gravity, and the motor now acts as a generator, driven by the falling weight, feeding that stored power back into the grid. They're essentially very large mechanical batteries.
interesting concept. Okay, so summing up this whole section on alternative sources, what's the big takeaway from the video? Can they replace traditional power?
The source comes down really hard on this. It argues that while wind, solar, and hydro are developing and they're important, they will not replace traditional centralized energy systems anytime soon. Not in the foreseeable future.
And crucially, this isn't just about politics or fossil fuel lobbies pushing back, according to the source.
No. The primary reason given, the fundamental technical barrier, is the lack of a revolution in energy accumulators, storage.
So the argument is, even if solar panels or wind turbines were practically free and 100% efficient, without a way to store massive amounts of power cheaply, efficiently, ecologically, and quickly.
Their growth as primary reliable energy sources will hit a ceiling. The source presents a breakthrough in storage technology as the absolute critical missing piece needed before we can truly rely heavily on these intermittent renewables.
Okay, that's a really strong statement. And it leads us neatly into the second major argument the video tackles, this whole concept of distributed generation.
Ah, yes, DG. And this is where the source gets particularly, let's say, critical.
So distributed generation, that's the idea that homes, businesses, small communities maybe become their own little power plants, right? Rooftop solar, small wind turbines, maybe biogas.
And they use what they need and potentially sell the excess back to the main grid.
Yeah. And the thinking behind it is often that if you have millions of these small sources all feeding in, you create a more resilient, decentralized energy system, less vulnerable to big power plant failures.
The source, well, it calls this idea a wet fantasy, specifically for people who don't fully grasp how large-scale energy systems actually have to function.
Wow, wet fantasy.
That's correct. Why such a strong dismissal? What's the core argument against it?
The video uses a pretty powerful analogy from biology to explain its viewpoint. Think about evolution. Life started with simple organisms, maybe with multiple, less coordinated systems like multiple nerve centers or something.
Okay.
But complex, highly efficient organisms like us evolve towards having one central brain and one central heart. Specialization and centralization for efficiency and control.
Right. So applying that to energy systems.
The source argues energy systems evolved in a similar way. We started with small, scattered local power plants serving just their immediate area, but the system naturally evolved towards large, highly efficient, centralized power stations connected by a powerful unified transmission network, the high voltage grid, because that's more efficient, stable, and manageable at scale.
And so trying to switch to widespread distributed generation, especially down at the low voltage level where we actually use the power, is like trying to deliberately revert back to having many small hearts in the source's analogy. It's seen as a step backward in terms of systemic efficiency and control.
Why is managing many small hearts so difficult in an energy system context? What are the technical problems?
Well, just like coordinating many small independent hearts would need an impossibly complex brain, managing potentially millions of small, intermittent, uncoordinated generators requires an immensely sophisticated control system, especially on the low-voltage distribution networks, the wires running down our streets.
Because those local power lines, they weren't really built for power flowing backwards from everyone's rooftop solar panels, were they?
Exactly. That's a huge point. They were designed for one-way flow from the substation to the consumer. But even more critical, according to the source, is what these low-voltage networks lack.
What do they lack?
They lack the sophisticated, real-time control and protection systems that are standard on the high-voltage transmission grid. Things like directional protection, knowing instantly if power is flowing the wrong way. Precise, second-by-second power flow control. And crucially, central dispatch systems that constantly balance generation and demand across the entire network to maintain stability.
And trying to scale those incredibly complex real-time control systems down to manage every street, every house, every unpredictable rooftop generator.
The source basically argues it's economically astronomical and practically unmanageable. It uses the phrase, "no brains will be enough,"
Yeah.
to illustrate the sheer overwhelming complexity of trying to coordinate millions of these little generators across the vast distribution network.
The video gives an example, doesn't it? A kind of failure scenario if you rely purely on distributed generation without that strong central grid. Can you walk us through their village example?
Yeah, it's a good illustration. Imagine a village, maybe 100 houses, and let's say 30 of them have their own generation rooftop solar, maybe a small wind turbine.
Okay, a reasonably high penetration of DG.
Right. Now imagine you disconnect this village entirely from the main high voltage grid. Maybe there's a fault upstream, a blackout. So the village is islanded, running only on its 30 local generators.
What happens next?
According to the source, chaos. Who's in charge? There's no single master generator setting the frequency for this new little microgrid. There's no central dispatcher telling generator A to ramp up slightly because generator B just went offline due to a cloud shadow.
So the frequency, the 50 or 60 hertz that all our appliances rely on, it would start jumping around wildly.
Exactly. It would fluctuate like crazy as individual solar panels switch on and off with passing clouds or the wind gusts and dies down. And here's the critical part. The inverters connected to those solar panels and wind turbines are designed with safety features.
To protect themselves.
Yes. If the grid frequency or voltage drifts too far outside the acceptable limits, which it absolutely would in this uncoordinated scenario, the inverters automatically trip offline to protect themselves and the connected equipment.
And if enough of them trip off because the frequency is unstable,
The whole local system collapses. Blackout in the village. The distributed generators, lacking that central coordination and the stabilizing inertia of the large grid, simply can't maintain a stable frequency and voltage together. They haven't learned to be friends, as the source puts it, without that overarching control system.
okay, that paints a pretty stark picture. Does the source concede that distributed generation can ever work in isolation?
It does acknowledge it might work in very specific, isolated microclusters. It mentions an example like a small, self-contained commune of maybe just 20 people.
But with major caveats, I assume.
Huge caveats. The source stresses this would only work if that tiny cluster is equipped with absolutely massive, dedicated energy accumulators. It uses the term wagon-sized batteries to act as a buffer and smooth out the intermittency. And, critically, it would need its own sophisticated, dedicated local dispatch system just to manage those few sources, the storage and the local load.
Right. But scaling that kind of solution, massive local batteries and complex control systems for every single village or suburban district.
The source argues the cost of doing that today is just economically unfeasible for widespread implementation across the existing low-voltage distribution networks. It's just not practical at scale currently.
So the takeaway is that DG can function okay, but primarily when it's connected to and essentially supported by a large, stable main grid.
Yes, precisely. The source uses this analogy. Selling your excess local power back to the grid is like a small stream flowing into a large, stable sea. The massive grid, the sea, provides the stability, absorbs the fluctuations.
But if the sea disappears, if the main grid goes down in a blackout,
Then those little streams can't suddenly form a stable lake together. They just become isolated puddles. They can't maintain the grid on their own because they lack the necessary collective intelligence, coordination, and the physical inertia that the large system provides.
this really underscores the source's main point, doesn't it? That you absolutely have to understand the fundamental physics and the complex layered control systems of large energy networks. It's not like the internet, where you can just route data packets around flexibly.
Not at all. Electricity is a physical system requiring real-time, instantaneous balance of generation and consumption, maintaining precise frequency and voltage across vast interconnected networks, and that requires sophisticated control at multiple levels.
The video even gives a real-world example of problems when trying this, right? Something about a district in Kursk.
Yeah, it mentions a district in Kursk, Russia, that apparently attempted to implement distributed generation within its existing 10 kilovolt medium voltage network. And the reported result was frequent outages and unstable frequency, basically,
Right.
illustrating the systemic challenges when you try to force generation onto networks not inherently designed for it, especially without adequate upgrades to control and protection.
Okay, so after detailing all these challenges, the storage issue for alternatives, the systemic critique of distributed generation, what does the source actually propose as the correct path forward for our energy systems?
Its conclusion is pretty clear. The fundamental structure should remain a traditional, centralized energy system. That means large generating capacities feeding power into the stable, high-voltage transmission grid.
So stick with the big power plants and big wires model.
Yes, but with a crucial difference. The key, according to the source, is diversification in the types of those large, powerful generating sources.
Ah, so not just relying on coal or gas.
Exactly. Develop powerful, large-scale solar farms, massive offshore wind farms, advanced nuclear reactors, enhance geothermal, more hydro where feasible, but keep the generation centralized at scale, connected to the high-voltage grid where it can be effectively managed by the existing sophisticated control systems. Don't try to manage millions of tiny, unpredictable sources way down at the low-voltage consumer end.
That makes sense. Centralized generation, but with diverse, cleaner sources. And the video hints that it plans to go into even more detail in the future on why this centralized, layered approach is so necessary.
It does. The source suggests a future video will break down the whole layered structure of modern energy systems. How power flows from generation through high-voltage transmission, steps down to medium-voltage distribution, and finally reaches us at the low-voltage consumption level.
And explaining how the dispatching and control works at each of those levels.
Exactly. And understanding that layered structure, the source argues, further clarifies why large-scale generation is technically most effective and manageable when integrated at the higher voltage levels of the network, not scattered throughout the lowest level.
Okay, so wrapping this deep dive up, what are the really core takeaways from this source for you listening right now? What should you keep in mind?
I think there are two main things. First, understanding that while alternative energy sources like solar and wind are absolutely vital for environmental reasons, they face significant technological hurdles right now, primarily. The lack of efficient, scalable, and affordable energy storage. That intermittency problem is huge.
Right. And the second key takeaway?
That distributed generation, while it sounds appealing and might have niche uses or supplement a strong grid, faces fundamental technical and economic challenges. According to this source, these challenges prevent it from realistically replacing our centralized grid system at scale, at least with current technology.
It really challenges that maybe oversimplified narrative you sometimes hear.
Yeah.
And it emphasizes that the complex physics and the really sophisticated system-level coordination needed for electricity networks are just non-negotiable.
Yeah, you can't just wish those complexities away. The source argues that simply adding more generation capacity isn't the whole answer. How you integrate and manage that capacity across a vast, interconnected system is absolutely critical for reliability and, preventing widespread blackouts.
It definitely makes you think twice about the incredible complexity behind simply flipping a light switch and having the power always be there.
For sure.
So here's a final thought building on the source. Given its strong argument about the necessity of a centralized systemic approach for stability, and acknowledging those real challenges of coordinating countless small intermittent sources, how do you think future energy systems will ultimately strike that balance? How will we balance the undeniable potential benefits of local generation with the fundamental physics and the systemic needs of providing reliable power for everyone?
That's the multi-trillion-dollar question, isn't it?
Yeah.
How to best integrate the new while respecting the physics of the old system. This deep dive certainly gives us a lot to chew on regarding the grid that powers our modern lives.